Another application of aqueous equilibria is the concept of buffers. So a buffer is a mixture. Okay, it's a solution that's made of typically either a weak acid and its salt or a weak base and its salt. And the point of a buffer, or the purpose of a buffer, is it's a solution that resists changes in pH when you add H plus or OH minus. It doesn't move. Its pH stays very, very still. Now, it might adjust a little bit here and there on one side or other, but never more than 1 pH unit. Okay. For example, if you look in this diagram here, if you have 1 liter of water, which should have a pH of 0, and you add 0.010 moles of hydroxide ions, say from sodium hydroxide, the pH goes up to 12, from 7 up to 12. Okay, 1 liter of water's pH is 7. If you have 1 liter of water and you add 0.010 mole of hydronium ions, or H+, it goes down to 2. But if you have a buffer solution, you have 1 liter of a buffer solution, and you add the hydroxide or the base, if your buffer solution pH, you see in the middle one, the green one, by itself is about 4.5. Look at how little the pH changes when I add acid or base to a buffer. That's the point of a buffer. So you may hear about buffered solutions or buffered aspirin. The whole point is to keep the solution from changing pH. Why might this be important? Well, biologically, buffers are extremely important. We don't want the pH of your blood or cell environment to change very much, because if it does, then things don't work the way they're supposed to, and the cell can die, or you can die. So here's an example. We have a buffered solution that contains 0.5 molar acetic acid, Ka value is 1.8 times 10 to the minus 5, and sodium acetate. That's the salt of the weak acid. So a buffer is made from a mixture of a weak acid and its salt, usually an alkali metal salt. So the acid is acetic acid, the ion, the conjugate base, is acetate, so the salt is sodium acetate. Okay, and we're going to find the pH of this solution. So the major species are the acetic acid, sodium ions, that's spectator ion, right? The acetate ion, and water. Okay, here's our ice table. We know that HC2H3O2, the acetic acid, dissociates into H plus and the acetate ion, and if we're looking for pH, we want the concentration of H plus. So our initial concentration of the acid was 0.5 molar, and the initial concentration of the base is also 0.5 molar. It's a mixture of these two. No H plus to start with. But some of the acid is going to dissociate a little bit, so that's going to go down by minus X. And a little bit of H plus will be produced, plus X, and a little bit of the acetate will be produced, plus X. This is a common ion problem, that's all. So at equilibrium is 0.5 minus X, X, and 0.5 plus X. We plug that into our expression for Ka, for the acid, which we know 1.8 times 10 to the minus 5, that's our Ka value. So concentration of H plus and C2H3O2 minus over concentration of the acid. We can make the approximation again because Ka is so small, we can make that approximation. We'd have to check it, all right? You'd have to justify that it's less than 5% of the original, but it is. Which we get then a value of X is equal to Ka here, which means the concentration of H plus is equal to the same thing as Ka, which means our pH is 4.74. So the pH of this buffer, which is made with equal concentrations of the weak acid and its salt, is 4.74. Preview of coming attractions. Since H plus and Ka are exactly the same, when our concentration of weak acid and base are exactly the same, then the pH is essentially equal to something called pKa. Remember, the little p in front of pH means negative log of H plus concentration. pKa means negative log of Ka. That'll be important later on. So what would happen to the pH of this buffer, the buffer we just created with 4.74 pH? What would happen to that pH if we added 0.010 moles of solid sodium hydroxide? Solid sodium hydroxide is a strong base, okay? And we're going to add it to 1 liter of this buffer. Well, now, we know that buffers are supposed to resist pH changes, so we shouldn't see too much of a change, but let's calculate it and be sure. Let's see what actually happens here, okay? So the major species are still acetic acid. Now we have some sodium ions, not important. Hydroxide ions, those are going to affect the pH. That's important. The acetate ion, that's part of our equilibrium, right? And water, which doesn't do anything, it's not part of our equilibrium because it's a pure liquid. So really what's interesting is going to be the acetic acid reacting with the base, the hydroxide base, to produce acetate and water. Now this hydroxide base is a strong base, so this reaction is going to go to completion. Okay? The strong base, the hydroxide, is going to react with as much acetic acid as it can to produce acetate and water, and it's not going to go back. All right, well, that's going to leave us with a little bit of acetic acid left. Right? We're going to use some of it to react away the hydroxide. The hydroxide is gone at equilibrium once this reaction is done. It's reacted with the acid. It's formed a conjugate base in water. So there's no more hydroxide at equilibrium. The acid has decreased by a certain amount. Well, it's a 1-to-1 mole ratio, so it's decreased by 0.050 moles, which was the concentration of the base. Okay? So we have 0.49 moles of acid left. We have no hydroxide left at equilibrium. And we do have now an additional amount of a little bit more of the acetate ion. Okay, I've got a little bit more than we started with. So now we know how much acetic acid is left. Let's see how much H plus is created from that. So we've removed a bunch of acetic acid from our original buffer, but there's still some left that's producing protons. So let's figure out how much is left. So our initial concentration now of the acid is what was left over, 0.49 in 1 liter, 0.49 moles per liter. No H plus, we already have 0.51 moles per liter of the acetate ion from that last reaction. So those are our initial concentrations. The change is the usual, and we have our new expression, which we can plug into our Ka expression, make the approximation, and we find out that our X value has not really changed all that much. 1.8 times 10 to the minus 5. Still very close. Now, if you use sig figs, it might come out to be exactly the same. If you don't use significant figures and you give yourself a little extra, you'll see that it does change by a little bit, 0.02 of a pH unit. That's tiny. Our pH hasn't really changed at all, and we added a strong base to it. So how does it do that? How does a buffer actually resist changes in pH? Well, it depends on what it's made of. If it's made from a weak acid and a salt, okay, it has large amounts of the weak acid and the conjugate base of that acid, which means that if you add base hydroxide, the acid is going to give protons to that OH minus to produce water, so you don't increase the OH minus concentration. Okay, if you add H plus to the solution, then the conjugate base, the A minus, takes in some of that H plus to form more acid, so that you don't have a buildup of H plus. Okay, so as long as the overall change is small, pH doesn't change that much. Now, can you overcome a buffer? Yeah, you can blast right through the buffer capacity if you add enough acid or base. But we're talking about, you know, minor amounts being added and not changing the pH. Remember back a few slides ago, I showed you what happens to just pure water when you add a tiny little bit of hydroxide and a tiny little bit of acid. The pH fluctuates wildly, but a buffer, it doesn't fluctuate very much with the same amounts. Okay, if it's a weak base and a salt, you have large amounts of base and the conjugate acid. And if you add OH minus, the BH plus donates H plus to it so that the hydroxide doesn't build up. And if H plus is added, the base, accepts the protons so they don't build up either. And again, as long as the change is small compared to the original concentration, the pH won't change. Okay, so this is kind of what it looks like. If you have the buffer made from the acid and base in equal concentrations, you've got a nice little even balanced solution. If you add a little bit of acid, then the base will absorb the extra protons and you'll produce a little more acid than base. And if you add extra base, then the acid will give it protons and the amount of acid will go down a little bit compared to the amount of base, which will go up a little bit. And the bottom here we have the equations that govern each of those. Okay, so the fact that you have a mixture of acid and base in the same solution means that it can go either way. It can adjust to either situation. We have a way of dealing with finding the pH of a buffer called the Henderson Hasselbach equation. This is just how you get it. We start with the Ka expression for a weak acid. We solve for H plus. We take the negative log of both sides, which is the little p, right? Negative log of H plus is called pH. Negative log of Ka is called pKa. And then the log of HA over A minus, but the negative log of HA over A minus, which we flip over to make the positive log of A minus over HA. And so we say that the pH of a buffer can be calculated by taking the pKa and adding to it this little log term of the concentration of base over concentration of acid. That's called the Henderson Hasselbach equation. Okay, so it's very useful if you have if you know the concentrations of the acid and the base in your buffer, and the value of X is going to be very, very small because Ka is very small. Okay? If you have the same ratio of acid to base, then the pH won't change. Okay, the pH will be the same as the pKa. So if the base and acid concentrations are equal, then you get log of 1, which is 0, and then pH is equal to pKa. So here's an example. You have 0.75 molar lactic acid. Lactic acid is an acid when you oxidize lactase, which is a common sugar found in milk. K is 1.4 times 10 to the minus 4, and you're mixing that with 0.25 molar of the salt of lactic acid, with sodium lactate. Okay, so we've got a buffer, but the concentrations of the acid and base are not equal. There's more acid in there than there is base. So since there's more acid than there is base, we would expect the pH to be a little bit lower than pKa value. Okay. Now we can do this traditionally, right? Our major species are lactic acid, sodium ion, which is spectator ion, not important, the lactate ion, and water, which is also not important. We can solve for Ka. Ka is equal to the concentrations. We set up an ice table as usual. Okay. We make the approximation, we solve for X, we get pH of 3.38. Or we can use the Henderson Hasselbach equation, which is pH is equal to pKa plus the log of base concentration over acid concentration. The pKa is the negative log of the Ka, 1.84 times 10 to the minus 4th, which is 3.85. And then the base concentration is 0.25 and the acid concentration is 0.75, so the log of that ratio there, we add that to the 3.85. Now it happens that that's going to be a negative number. Log of 0.25 over 0.75 is going to be a negative number. So it ends up subtracting from the 3.85, and you get 3.38 as well. So Henderson Hasselbach is very useful if you know the concentration of the base and the acid of your buffer. You can find the pH of the buffer. And you can then use it if you do shifts in concentrations. You can use Henderson Hasselbach to figure out what the buffer is going to do. Okay, so buffers are important biologically. They're important in chemistry to keep the pH from changing, because too much H plus or too much OH minus in solution may interfere with a reaction. So we often will use a buffer to stop things from changing, so that it doesn't throw a wrench into our reactions. But definitely in biology, if you go on in biology and you do biochemistry, because the environment of cells is so delicate and easily affected by its surroundings, we want to make sure that we don't change the environment's pH too much, because then things like proteins won't work. And if proteins don't work, the cell dies, and then the organism dies. So buffers are very important in biology, biochemistry.